A ball 3 kg has a potential energy function where x is measured in meters and u potential energy given by this formula, a cubic function. The following graph is sketched on the potential energy function. Energies indicated on the vertical axis are evenly spaced. X1, have X1, X1, X3. No, I mean E1, E2, E3 are evenly spaced, meaning E2 minus E1 equal to E3 minus E2. Energy E1 equal to U, potential energy at the position X1 and E3 is at X3. Determine the numerical value of X1 and X3. X1 and X3 numerical value. Okay, equally spaced. So plugging the formula here, X1, X2, X3, and use this equation. Try simplifying this equation to find the value X1, X3 here. Here at the bottom, this is the local minimum. Therefore, the tangent there is horizontal, and the gradient of the tangent there is 0. So we can take the derivative of the energy function with respect to x, and at that point x1, the minimum, this derivative will equal to 0. This derivative is the slope of the tangent at that point. Okay, derivative of this thing, it is equal to 3. 3x minus 1, derivative is 3, and then minus 3 times x minus 3 square, and then times x derivative, which is 1. So just simply like that. This thing equals to 0 at x1. Okay. We can divide 3 on both sides. So 1 minus x1 minus 3 square equal to 0, meaning x1 minus 3 square equal to 1. So x1 is 4. X1 is 4. There's another solution, of course, which is 2. Or x1 is 2. X3 maximum again. Okay. So x1 is 2 and x3 is 4. This value is x3, because it's greater than x1. X3 is 4. And x2 is 2. X1 is 2. Okay. Describe the motion of the particle if its total energy is E2. Total energy is E2. Let me write a dash line. Can I draw a dash line there? Horizontal value like this. Total energy. Total energy. Describe the motion if its total energy is E2. Meaning right at the middle of E3 and E1. Describe potential decrease and then increase. There must be another kinetic energy. Yeah. The kinetic energy. Just take the E2 here, which is a constant, and then subtract the potential. You have the kinetic energy. So what does the graph of kinetic energy looks like when you take this constant and subtract this graph? Minus of a function. We have a function u, and then you put a minus sign in front of it. It will be reflected in the horizontal direction. Vertical direction, like this. Right? And then the constant, which is E2, in front of it. Let me illustrate that on the desk motor, and then I should take a screenshot and put it in. It's nice. Change the share screen. Here, the function of the energy is 3 times x minus 3 minus 1. Minus 1. And minus x minus 3 or skip. Okay, the function like this. This is the function of the potential energy. Okay, change the up to sig, and here minus sig. There. Wait, this is sig, not 16. There. And if I take the this is maximum, which is 8, minimum is 4. So the we can find those value, right? Yeah, we can find the value x x3 and x1 here already, meaning 2 and 4 respectively, and then plug in back into this equation. We can determine the numerical values of E1 and E3. E1 is 3 times of x equal 2 here, minus 1, and then minus 2, minus 3, keep, it will be equal to the minimum value here on the dashboard. That is 4 joule. Similarly, E3 will be equal to 3 times of 4 minus 1, minus of 4 minus 3, for keep, which is 8 joule. And therefore E2, which is in the middle, E2 must be 6 joule. Okay?
Yeah.
And so when I plot the new graph, which is 6 joule of the total energy minus this thing, this blue graph is the kinetic energy. Okay?
Yes.
And to have these two types of graph, you use a graphing calculator. What type of calculator do you use? TI or Casio?
TI.
TI. I have one TI thing here. This one, Casio as well. Okay. Yes, you can use the TI calculator to plot the graph of kinetic energy. This one. Okay. And from this blue graph, we can describe the motion of the object. So we see that the energy, kinetic energy decreases, and becomes 0 here. The part between A and B is called a potential energy well. Basically, it's a well. And when we have a well like that, meaning potential decrease and increase, it means the object oscillates. And at point B here, the kinetic energy becomes 0, and therefore it must move. Must move backward. And therefore, the object oscillates between A and B. And that is a if condition in the question here. If its total energy is E2, the potential energy cannot increase to the new value here when the kinetic energy becomes 0, so that the total energy is E2. So the question B here is a different case. We don't have this kind of part of graph. Okay, just go down up here, and the kinetic energy decrease until 0 here. So this point is 3 sig, and this point is 1.27, and of course sig, because this is the value of sig. The maximum here is 8, and the minimum value is 4. The kinetic energy. Okay, again. Question B. The function of the kinetic energy is 6, which is E2, minus 3, x minus 1, plus x minus 3 cubed. And this kinetic energy decreases to 0 when x equal to 3. Okay, between 1.27 and 3, or meaning between the 2 points, between x equal 1.27 and x equals 3, the potential energy is a well, and the kinetic energy here becomes 0 here. This is the key, becomes 0 here. So the object oscillates. Between those points, Of course, we do not have the part of the function on the right. Sketch the graph. Question C. What is the particle speed at x1 if its total energy is equal to 58 joule total energy? Okay. Take this total energy 58 and then subtract the kinetic energy at x1. We need to find x1 first. X1 here is when the energy is E3, and E3 is equal to the maximum, which is 8 joules. Total energy is 58. E total is 58 joule at the point x1. Okay, at x1 here, the energy, potential energy U, Ux1 equal to the minimum 4 joule. And therefore the kinetic energy is 58 minus 4, which is 54 joule kinetic, equal 1/2 the mass of the object times its speed square. Yes. Do we know the mass of the object? No, 3 kilogram. Good. 3 kilogram here. It's a very important equation. So we can find speed easily, Yes. So the speed is 2 times of 54 over the mass 3 kilogram, and then take the square root. Question D. Sketch the graph the particle acceleration as a function of x. Acceleration. We should indicate x1, x3 on your graph. As a function of x, acceleration. A force over mass, but we don't know the force. Position, as I remember, position is the differentiation of. No. There's something I miss memory. Something differentiation of the potential energy here in terms of x. We get the tangent, and what's the meaning of that tangent? The gradient of potential, not with time, but with x with position, and that differentiation means something that I forgot. I think I can check it back at my scheme. Yeah. Here. That is the force. Yeah, that's what I was looking for. Yes, the force. So one more thing that you have to remember is relationship. Differentiation of the potential energy with respect to position x is the resultant force. Yes. Let's check if it is given, the formula in the booklet. No, I don't see it. Okay, here. Minus dV over dx. V here means potential in electrical part, but we do not study that electrical, but only mechanics. But it meaning is the same, meaning this, wait. V potential, and E here is the field. And when we multiply the field with the charge in the electric part, wait, is it electric part? Yeah. In the mechanic, do we have the similar relationship? PE, what is this one? Energy over time. Yeah, physical power, but in the form of a differentiation, Power. Okay, that relationship is in the electric part here, not the mechanic part, so you have to memorize this one. The force is the differentiation of the potential energy with respect to the position. And then take the force and over the mass, we get the acceleration, Okay, do it. Again, the formula of the U, question D, Ux is x minus 3, x minus 1 3 times, minus x minus 3, keep, and the force variation with position is minus of the differentiation of U with respect to x, taking this differentiation again, that is 3 minus 3 x minus 3 square. That's it. This is a quadratic function, and the minus sign in front of it. So we need to put the minus sign here. Okay. And the final result is 3x minus 3 square minus 3. This is the vertex form, right? So this graph is a parabola like this. That's the vertex, and also you can find the x-intercept to state the graph more accurately. Have to find the two x-intercept. Of this, the ratio, okay. Acceleration is what we need to draw the graph. Acceleration is the force over the mass. Taking this thing, the mass is 3 kilograms, therefore the function here is 3 kilograms. The function of acceleration is x minus 3 square minus 1. Okay, so the vertex of the graph of acceleration is 3 minus 1, not 3 minus 3, huh? Okay.
Yes.
And then find the two x-intercepts. To find that x-intercept, of course, you can use a calculator or convert it back, find the solution. Okay. Anyway, for y to be 0, x minus 3 square must be equal to 1. For this thing to equal to 1, x is 4, huh? X is 4, or x is 2. Yeah, so the two x-intercept is 2 and 4. 2 here and 4 here. Okay.
Yes.
And 3 in the middle, exactly, because the vertex must be in the middle of the two x-intercept. Right in the middle, 3. Good. So this is the graph of acceleration, huh? This is the position. Let me complete that graph by completing the exit. And an acceleration like this also means that the object oscillates. Wait, oscillate means acceleration must change direction. Yeah, not oscillate, must change direction when changing from being positive to negative or vice versa. E. The particle is released from rest at x equal 1/2 x1. Find its speed as it passes through the point x equal x1. Released from rest. Okay, it is released. Start moving, huh? It start moving from x1, 1/2 x1. 1/2 x1. So the kinetic energy there is 0. And therefore the total energy is equal to the potential energy at that point, which is E3, at 1/2 x1, which is A joule that we calculated in the question A. Okay?
Yep.
Total energy is that. And at the new point, x1, according to the graph, E energy, let me check that graph here. At x1, potential is minimum, which is 4. The potential energy, PE, at this point, equal to E2 at this point, x1. Is that E2? No, not E2, but E1. E1 at x1, which is 4 joule. 4 joule. So the kinetic energy gain, the kinetic energy increases by 4, huh? From 4 degrees to 4. The decrease of potential energy is 4 joule. Decrease in potential is 4 joule. Then the increase of kinetic energy is 4. Okay.
Yes.
The kinetic energy increases by 4 joule. Increases from 0 to 8 minus 4, which is 4 joule. Okay.
Yes.
And that kinetic energy at x1 is 1/2 of the mass times the speed there at x1 square. It equal to 4 joule. The mass is 3 kilograms, and then we can find V1, huh? V1 is the square root of 2 times 4 here, and then divide the mass 3 kilograms. 8 over 3, huh? Square root 8 over 3. So we can take a, a close value, 8 over 3, rounded, 1.63 meter per second. Okay, 1.63 meter per second. That's it. This 3 is the mass. Yeah, so it has nothing to do with the acceleration. Actually, it does relate to the acceleration, but we don't know the relationship between acceleration and time. This is the relationship between acceleration and position. Okay, yes. A and x, not a and t. Therefore, we cannot do the integration. A few more minutes, huh? We can try doing the last one. Oh, the only 2 questions, so it could be done. The total force 6 kilogram object is given by this equation, which is a function of position, linear function. In newtons, the object is moving 2 meters per second at the origin. Determine the work done on the object by the force when it moved 4 meters from the origin to x direction. Easy. So lucky, huh? It's easy. The work is defined as force times displacement, but in this case, the force is not constant but vary with position. Therefore, it's a function, and therefore we take the integration with the position. Okay.
Yes.
Right again. So this is the method in ABC. Work is integration of force function with respect to the infinitesimal movement, displacement dx, taking the displacement from 0 to 4. That are the limits, the boundaries of the integration. This is a simple function to take the integration 3x plus 5 dx from 0 to 4. Easy enough. 3x squared over 2 plus 5x, huh? And put the limit in 0, 4. 3 times 4 squared over 2 plus 5 times 4, huh? Which is here 44 joule. 44 joule. Okay. Question B. Determine the speed of the object when it has moved 4 meters. Move 4 meters. The speed. Work done. Okay. Again, relationship between energy and work, huh? Because they didn't say anything about the change in the height of the object. So we assume that the potential energy does not change. Okay.
Yes.
This is the force. Yeah. They didn't say anything about it going up or down. So we have to assume that the height does not change, and therefore the kinetic energy stays the same. And work done by this force, 44 joule, will be equal to the increase in kinetic energy of the object. That the object moves horizontally, so that the potential energy P is constant, and therefore the work done by the force is equal to the increase in kinetic energy, meaning 44 joule. 44 joule equal to 1/2 of mv squared final minus initial kinetic is 0, huh? Kinetic energy initial starting from rest. Moving at the origin. Oh, at the origin it was moving at 2. Okay, 2. So initial kinetic is not 0. Sorry. 1/2 of the mass times 2 squared. Do we know the mass? Supposedly yes, 6 kilogram. Okay. 6 kilogram. Therefore, we can find V by solving this equation with the mass being 6 kilogram, huh? Easy to find V, right? Just take the final answer, 4.6 meters per second, huh? Okay.